to 51st lecture on network theorems, network analysis, and let me just very briefly review what we have done so far. We started with simple KVL, KCL with DC supply, then there will be energy storing elements present in general in a network, inductance and capacitances, and they invariably give you differential equations when you write KVL, KCL, etc. And to solve for currents, classically we solved those differential equations and got the current response and so on. Then I covered another important topic, that is apart from being in time domain solving differential equations to get the responses, you can alternatively solve a network problem by going to S domain. The advantage of that is those differential equations get transformed into some algebraic equations, and we can invoke whatever laws, see KVL, KCL or see nodal analysis, all those techniques which we applied in DC circuit analysis can now also be applied to S domain circuit straight away. Why? Because V s is equal to I s into Z s in the same way as V equal to I r. Therefore, all those rules can be applied, and this can be applied to linear time invariant networks. And of course, we assumed when we did S domain that everything starts at t equal to 0, your input signal you are applying at t equal to 0. So, causal signals are there, system is causal and so on. Now, we are going to start some network theorem. Henceforth, therefore, and Laplace transform, when you get say I s, then you should take the time inverse of that Laplace transform to get the time domain expression, because our goal after all everything is real and time dependent. I applied so much voltage as t equal to 0, what will be the expression of the current? Then you have to take the inverse transform to get the solution, and this solution will be same as the classical differential equations. I mean, comparing these two methods, it looks like okay, Laplace transform method does not give, I mean very straightforward, steps are known, but only problem is when you take the inverse, you have to be little bit careful, properly expand the I s. Suppose I am interested to know the current in some branch, that I s will be equal to some function of s into V s. You have to take the inverse of that. To do this, you have to correctly expand that expression in terms of partial fractions, and there some time gets consumed. But in classical way, the beauty is you can after writing down the differential equation, you know what are the terms which will be present. Okay, constants are to be determined, that is fine, depending upon repeated roots, equal roots, this, that. I can, looking at the differential equation, straight away write down the nature of solution. Then some constants are to be determined from initial conditions or so. So, both these approaches are important. Particularly Laplace transform method assumes importance, because you will learn also control system theory next time. They extensively use Laplace transform. Laplace transform straight away gives you the transient as well as steady state response. So, with this background up to that we have got. Now, I will start some network theorems, interesting network theorems. There are several. One is called superposition theorem, superposition theorem. Then you have Thevenin's theorem, very popular method, Thevenin's theorem, Thevenin theorem. And then there will be several others. I am just listing these two for the time being. Superposition theorem can be applied only to linear networks, that we must know, and henceforth these networks always I will write something like this in S domain. What is the point? See, V s is there, there is R, if R is there R, there is R 1, this is R 2, then S L R 2 and this is S L, and here is R 3. There may be a capacitance also present, I do not mind, because I know what is to be done, 1 by C S. Like that the network henceforth I will draw. That is, I will treat this as some Z 1 S. Of course, pure resistance is R 1, this is R 2 plus S L, Z 2 S, Z 3 S and so on. And then whatever method you want to apply, you can apply. And suppose there is another voltage source here, another suppose voltage source is here, this is suppose V 1, there is another voltage source which may be V 2 S. Okay. If in a circuit more than two sources are present and there may be another, suppose I say that there is a current source also present like this. I s. So, a network can consist of several voltage and current sources. Here 2 voltage sources, 1 current sources I have drawn. Now, superposition theorem tells me, okay, you can solve this network considering all sources present at a time by maybe if you adopt mesh analysis, then assume the current, solve for them, or nodal analysis, assume the node voltages and solve for them. This is suppose R 4, this is R 5, that is fine. But superposition theorem tells you that suppose you are interested to find out the current in this branch, what is I 4 S? Then superposition theorem tells that you consider, you draw the circuit with one source at a time, that is, and replace the other source by its internal impedance. For example, in this case a voltage source V 1 S is there. For V 1 S, only V 1 S is present, like that you treat, only V 1 S is present. Then redraw the circuit. So, it is R 1, it is there. Now, this should be replaced by V 1 S is here, should be replaced by its internal resistance. If nothing is there, short them, then this is R 2. Very quickly I will tell, you know this thing R 2 S L, R 2 S L, and then only V 1 S is present. Okay. Then V 1 S should be there. I have assumed V 1 S is present, only V 1 S, and other sources, that is V 2 S and I S, should be replaced by their internal impedances. So, here the internal impedances will be these 2 points where V2S is present, I will replace it by short circuit, and then R3 is of course there, R3 I will draw, and then 1 over Cs, these are impedances. So, 1 over Cs, that is fine, R4 will be there, R5 will be there, and this current source should be replaced by its internal impedance. Between these 2 points it is an ideal current source. Its internal impedance is infinity, so it should be replaced by open circuit. Now, in this network only one source is present. Therefore, I will calculate the current flowing through R4, that is this current I4, I will find out. Due to V1s alone, say this is I4 dash test, I say. Similarly, I will calculate I4 double dash test due to V2s alone, replacing other sources by their internal impedances. I am not redrawing, you understand. Then this will be shorted, here V2s will be present, this Is is also absent. So, that will be, you have to solve once again. Then find out I4 due to the current source, due to Is alone, only this Is will be present and this should be shorted. And then when all of them are present, I4s will be equal to I4 dash test plus I4 double dash test plus I4 triple dot S. This is called superposition. So, linear network superposition theorem is an important tool. Sometimes may not be for solving the networks, because you see this network, if you solve all the sources are present, compared to this, for each of the sources network is slightly simplified. For example, this source is not there, okay, but you have to calculate each time you have to solve this network. So, for example, this was for calculating I4 dashed. Then the next one, let me redraw. The second one, this is this. To calculate I4 double dashed, very quickly I will draw. It should be only due to V2s. So, V1s is present, so that you get visually what is happening, how the network topology, not topology, how it gets a bit simplified. R2, this is SL, impedances should be present, same impedances, and here only V2s is present, plus minus V2s, and then 1 over Cs is there. Very quickly let me redraw, so that you do not miss any point. Here R4 and here R5, because these two are open circuited. This is for I4 double S. Then the third one is to calculate I4 triple dot S. What I should do is this, only Is is present. So, voltage sources should be replaced by a short circuit R1. This is R2 SL, and then here there was some resistance, R3 was there. Correctly draw the circuit. So, here also it is shorted between the source, then R3, and then some 1 by Cs is there, it should be shorted, and 1 by Cs, and then R4, R5, and only the current source is present. So, and then I have to add this plus this to get the current flowing through this I4 in this network where all the sources are present. But nonetheless, you have to solve the network for 3 times, although you have to handle with one source at a time. That is there, but the idea of superposition theorem is to understand many circuits, to establish many theorems of network analysis. This is adopted quite often. Okay? Understood this point. So, that is what superposition theorem tells us. Therefore, a network may consist of several sources, including both voltage and current sources, and I know how to solve it by applying superposition theorem. It is slightly lengthier process, it looks like, compared to if you consider this whole network as it is. That will be slightly complicated compared to each one of them, that is fine, but here you have to apply 3 times to solve the networks. I think you have got the point. So, that is the idea. So, superposition theorem, it is also true that it is needless to say, but still I am telling that okay, for 2 sources present, third source is absent, you find out the currents, and then only third source is present and other 2 sources are absent, you can also the result will be same. Add these 2, you will get I4s. Got the point? One may say that okay, so superposition theorem tells that one source at a time, that is fine, but what I am telling, 2 sources I will take V1, V2, Is is absent, I will find out the current. These 2 together will be only present. Similarly, when Is is present, these 2 should be replaced by their internal impedances, calculate the currents, add this up and you will get some I4s. Here I showed you how to find out currents in a specific branch by applying superposition theorem. And also another disadvantage, should I say disadvantage, I am not sure, but you try to understand this point. This is only for this branch I am doing. To find out this current I have to solve. Similarly, to find out another branch current, all the branch currents when one source is present is to be solved, is not? It looks like okay, if you are interested to find out one branch current, perhaps superposition with 2-3 sources may be a good choice, that you have to work it out. But if I ask you in this network solve currents for all the branches, then for each of these networks when V1s is present, you have to solve not only for I4 dash test, but also I1 dash test, I2 dash test and so on, in this branch also like that. So, computational overhead will become looks like higher. More complicated the network is, more time consuming it will be, but nonetheless superposition theorem helps us to understand several other interesting theorems. That is what we are going to do it. Before, next thing is Thevenin's theorem, one of the most important theorems in network analysis, and before doing Thevenin's theorem I will first tell you about one very interesting observation about networks. Okay. That is, should I call it, I mean some people call it substitution theorem, one substitution theorem. This theorem, what is the statement or what it is actually, to make you understand this, I will take a simple network to tell you about that. Suppose you have a network like this, simple network. I have taken the values such that the calculations become easy. Suppose you have a network like this 5 ohm and this is 4 ohm and this is say 0.6 ohm and this is say 30 volt. Okay. This network can be easily solved because this is 6 ohm parallel with 4 ohm. So, current, this current in the circuit is very straight away 30 plus 0.6 plus 4 into 6, these two are in parallel 4 and this 6 by 10, which is equal to 30 by 2.4 plus 0.63 is equal to 10 ampere, is not? This current is known. Okay, if this is 10 ampere, this is 10 ampere, the other currents in this branch will be this 10 into 4 other resistance divided by sum of this resistance 10, that is 4 ampere. This will be 4 ampere, this is 10, so this must be 6 ampere. Okay. Now, consider this network. What I am telling, I can solve it by any method, nodal, mesh, but I have, because the values are so simple, series parallel things are there, why should I go for those methods at all? So, I have solved it numerically. Now, what this particular substitution theorem tells that this network, what are the thing, what will be the voltage drop across this resistance? 6 into 4, 24 volt. Let me write it with other color, 24 volt. What will be the voltage drop between these two? Current is flowing like this, so this is 6 volt, 10 into 0.6. What will be the voltage drop here? Plus minus 4 volt. And what is the voltage drop here? This is 20 volt. Is not? This is the thing. I know, I have solved the network, I know everything, ins and outs of the networks, currents in various branches, this, that, voltage across each element, so on. Now, I redraw another circuit, listen this point carefully and say that this is the network, this is 30 volt and here is another network, this is 1 ohm and here is another impedance was there 5 ohm and here I will just connect a battery of voltage 24 volt. So, this network does not look exactly equal to this network, same as this network, because there was a 4 ohm resistance here. Here is a 24 volt battery I have connected. All the impedances and other sources I have kept as it is. Now, the point is these two networks, in these two networks, all the branch currents will remain same. That is, voltage drop across this element was 24 volt, replace this by a 24 volt battery and redraw this network, which is non-existent. This is the actual network given to me. But what I am telling, in this network, if you see what will be the current in this branch? Voltage 30 volt, with respect to this point, this is 24 volt. So, 6 volt will be there, 6 by 0.6 is 10 ampere. These 2 points voltage is 24 volt between these 2 points, 24 volts. 24 by 6, 4 ampere will be there and 6 ampere is there. Therefore, currents in each branch of this network and various node voltages will are same as in this network. It is an observation. That means, given a network, you can replace a resistance after you have solved it by the voltage drop and by a battery, say for example, no change. Similarly, I could say that let me redraw. This is 30 volt, this is 30 volt, this is 0.6 ohm. You have suppose replaced it by a 24 battery, 24 volt battery, and here how much is the voltage drop? 4 volt plus minus. If you wish, you can write it as a battery with 4 volt. Keep it as it is. Here also everything will be same. The current distribution in this network, this will still remain 6 ampere, this is 10 ampere, this is 4 ampere and so on. Therefore, voltage drop across any impedance can be replaced by a battery whose strength will be I into Z, that voltage I into R in this case. Similarly, I could do also this one. After learning this, I will say, look here, it will be like this. You have a 30 volt battery, very interesting observation I am telling you. This is the original network, these are my thought process, okay, this network and that network, so far as branch currents are concerned, exactly they will remain same. Similarly, here I could say there is a current source of 6 ampere. And simultaneously you can do this one also. This is, suppose I say this is 4 volt a battery. That 1 ohm resistance, this is replaced by a 4 volt battery, because 4 into 1 is the 4 volt. This 4 ohm resistance through which 6 ampere flows, I have replaced it by a current source 6 ampere, and other impedances I keep as it is. Then also the current in this network, if you solve, it will remain 10 ampere here, this is 6 ampere in any case, this is 4 ampere, and I can easily verify this is 24 volt plus 4 volt 24, node voltages will be also same. Therefore, either you can replace the impedance by a current source or a voltage source. The currents in various branches of the network will not change, and it will be there. Now, the question is, okay, this is a very good observation. That way also it can be looked at a circuit. You can this circuit, this circuit, this circuit, they are all one and the same so far as the current distribution are concerned, but they are not identical circuit, because 4 ohm is replaced by a source 6 ampere. That is my botheration, I must know what I am doing. If that be the case, then what is the use of this? And this I can do, it looks like if I have solved the network, then I can do it. No, not really. This particular theorem can be applied very nicely to solve several network theorems. Okay. For example, I will apply this to for example, to find out the currents. Suppose I am given a network. Now, I will go for general circuit. It is a general statement of this. You go to any circuit, for example, here any network, you go some network, let me write here is a voltage source, things like that, here is another resistance, another voltage source, another resistance, what not, like this, a network is there. Now, what I am telling, I am writing now general thing, plus minus, this is plus minus, voltage I do not know, R1, R2, R3, and this is suppose plus minus C2, and this is suppose R4. Okay, in this network I can assume these currents to be I1, suppose the I1, this is suppose I2, this is suppose I3, then what I am telling in general this circuit will be same as E1, suppose I have not disturbed here. If I wish this voltage, I can simply write a battery like this, I1 R1. Currents in the various branches will not change. Got the point? Similarly, this branch you can replace it by a current source if you wish, I2, and here if you wish you can change, I have not changed, it is my prerogative, it does not matter, and here is a battery and suppose this one. Once again what I am telling, this R1 is replaced by this battery with this voltage, magnitude of the voltage is I1 into R1, that is important. Similarly, this way. So, if you replace it, these two circuits are same so far as the various branch currents are concerned. We will use this extensively to prove various network theorems in our next class. Thank you.